Welcome to the second part of my presentation. So now let's have some information about indoor location application. Under the context, I can define three contexts of application. So first one is commercial and economic application. Fire on the military operation, on security in the buildings. So when you use commercial and navigation application, so you need to have some access point inside the building, permanently linked to the network with electricity on the network for long-term usage. And then you can indicate the coordinates of each access point in a manual form. For fire and military operation, you need to go quickly on a building, and if the building does not include any system for indoor location, so you need to deploy it immediately. And it's for short-term utilization. So because you cannot go inside the building before, you have to deploy your access point outside the building using a battery and a wireless network. And for the security in building, you need to locate all the devices which are from the company or out the company in order to follow your employee or people which are unknown. So what type of properties we need for indoor positioning? So we need, of course, accuracy, but not only for the mobile. And we need sort of availability of the system. We need to have the system working at any time, always working on. We need also to have some integrity in order to be sure about the coordinates in specific application. We also need to have security on the authentication, on confidentiality of the data exchanged in order to protect the coordinates calculated in the system. We need also adaptability of the system when the environment is moving. It's not always the same type of environment. So if you want to manage your accuracy, you need to have some adaptability. And also the coverage is important in order to define the density of access point you need to deploy. So in order to do some indoor localization, you need to use some input. You need to use some specific techniques such as a radio system, inertial system, ultrasound system, or camera system. For radio system, you can have at least two or three solutions. So it can be a signal strength on the received signal. It can be measurements of time of flight. And for camera, it can be artificial or natural markers, and also simultaneous location and mapping in order to follow the devices. So when you have an homogeneous area, you are going to have some radio signal strength which can be defined in advance using a model. You can use trilateration to calculate the coordinates. You can use some simple model like the Friis equation, and also in order to have a good accuracy on such context, it will be interesting to have feedback information if it's possible, but it's not fully necessary. So on an heterogeneous area, so the signal strength will be difficult to be analyzed to define correct position, and we have some very high rate of multipass, which is fading and fast fading, and this is difficult to take into account in the model. Then you have also variation of the context in short term, because people are moving inside the building, and doors or windows are open and closed, and also for long-term point of view, you can also add and remove partition inside the building. You have changing ways of electricity or water. You have some furniture which are moving, and you need some adaptation to a good propagation model. So if you don't use any feedback function, you are going to have a weak accuracy in such an environment, and you need feedback information or an a priori measurements, which is a benchmark. So this is an example of an heterogeneous area. So on a corridor, you have no wall from the left part to the right part, and when you are on a room, you are going to have a lot of walls from one room to another one. So it is quite difficult to differentiate these two environments. So what about radio solutions for indoor positioning? So one of the possibilities is to use fingerprinting. So that means you have to collect many information about a lot of points inside the building, and you have to associate a value or a color in order to visualize if you are far or near from an access point. But you can also use standard propagation formula, but according to the building, you can introduce a lot of errors. So in GSM or ultra wideband network, you have the ability to measure time of flight, and using such measurements, you can also have information about the distance between one antenna and the device. So you have time of flight, time of arrival, and the time of differential of arrival. So this is three different solutions to measure distance using time. So you can also use dedicated device which will use exactly the same frequency as the satellites, which is called the pseudolith. And if you are deploying this inside the building, you can locate the smartphone or the device, the mobile device, inside the building. But you need to have the right to send information on such frequency. So one of the other solutions to do indoor positioning is to use inertial units called IMU, inertial measurement unit. So it's an interesting way of measurements movements inside the building, but it is only a relative system. It's not an absolute system. So you can say that you are going to move from one point to another one, but the error will be cumulative because you don't have any absolute coordinates. It's only relative position, which depends with the last points, the last calculated point. So for ultrasound measurements, it's roughly like a radio system. So you can send information from one fixed point to a mobile receiver, and you can measure distances between the sender and the receiver, because the sound speed is less than the light speed. It is easier to measure distances using sounds, but the sound and the ultrasound don't cross rules on obstacles very easily. So now the camera and the recognition and the identification of area using cameras, which is called SLAM. So the idea here is to define on the picture, you can identify some well-known points in order to know in which orientation and direction you are by analyzing the picture. So this is a description of how it works. So according to the size of the artificial marker, here it's a tag, according to its size you can determine the distance, and according to the perspective between the camera and the picture you can define the direction vector. And with these two information, if you know the coordinates of the tag, you can define where is the camera compared to the tag. So this is a synthesis of indoor positioning system, and according to the system you are going to use, if it's GSM or 3G, if it's GPS, Wi-Fi, differential GPS, camera, and the inertial units. So with inertial units, it can work indoor and outdoor. You will have something like centimeters of accuracy, but like I said, it's only relative position, it's not absolute. So this system needs to be linked with an absolute system in order to have good results. So for camera, you can use it indoor and outdoor. You need to have good lighting condition, because on the night it's not possible to use this system, except if you are going to use infrared cameras. You need also to have good color variation in the environment in order to differentiate easily the different part of the picture. For DGPS, it is working only outdoor. For Wi-Fi, it is working mainly indoor or near the building, which can be outdoor but near from buildings. And for GPS, it's also outdoors, like GSM, which is also working in part of the building, but not everywhere. But also what is difficult for GSM is to receive more than one antenna inside the building. So what about the Wi-Fi, which is an open frequency? Anybody can deploy Wi-Fi access point and the first Wi-Fi access point can be used at the beginning of 2000, but it was in a closed operating system. But then in 2004, the first Wi-Fi access point with an open system arrived, and it was called OpenWRT, which is an embedded Linux specifically built for such equipment, because you don't have a lot of CPU, you don't have a lot of memory, you need to have a very small piece of Linux. But from this point, it was quite easy to include some additional piece of software in order to build a localization function inside the access point. Previously, it was not possible. You need to have a contract with a company if you want to add some piece of software on the first Wi-Fi access point around 2000. So we started research activities on indoor positioning area, something like end of 90s, sorry, and the beginning of 2000. So indoor positioning infrastructure centric started from the year 2005. So because the Wi-Fi signal is bidirectional, the location function can be in the infrastructure or in the mobile device. It depends of what type of application you want to use, but both parts can be used to receive the signal from the other. A contrario, in GNSS signals, it's only unidirectional, so it's only from the satellite to the user, to the ground device. So the ground device is only the receiver, on this ground unit cannot send any signal to the satellite. So it's really, you are locked. It's only calculation system inside the ground mobile device. So with Wi-Fi signals, there is 3 ways to develop a location service. So you can use mobile-centric solution in order to have all the calculation inside the mobile device, but you can also have an infrastructure-centric solution where all the calculation will be on the network, on the access point, but it will be a distributed system, because it's no more centralized, it's distributed, because the reception will be on more than one device. Both solutions can be also used, because it's not because you prefer for your application to have a mobile-centric solution. You can use both at the same time, probably to improve the confidence and the integrity of the results. So how is working the mobile-centric solution? So the mobile-centric solution is quite difficult to develop, because you need to access very low-level information on each mobile device, such as iOS, Android, or Linux, for example. And because you don't have an easy access, you still have a hard task to collect this type of information. For example, for many years in iOS, it was not possible to collect this information. It was blocked. Now you can manage a contract with Apple in order to have access to this information. So it's not as easy as we hope about getting information, about getting this type of information. But the advantage is sending a signal from one access point on all the mobile devices will receive this information. So it's probably easier to have a scalable solution using a mobile-centric solution. So for the infrastructure-centric solution, now you have one device which sends one packet which is received by more than one access point, at least 3, and with these 3 receptions you are going to have the ability to calculate coordinates for the mobile device, and then you have to send this result to the mobile device. So the advantage is you send only one packet to localize one mobile device. But if you have more than one smartphones or mobile device, you will need to send at least one packet from each mobile device in order to compute and calculate one coordinates. So what type of access point can we use for this infrastructure-centric solution? So the first one, which were with an embedded Linux, was the Linksys WRT54G, which is the first one with an embedded Linux. And then there was also Fonera Wi-Fi access point. But today you can use, for example, Raspberry Pi computer in order to transform it as an access point. Adding Wi-Fi device, it's better because of the chipset. Can explain why the Wi-Fi chipset embedded on the Raspberry Pi is not usable because the driver is not sufficiently accurate to deliver the signal strength. And now there is also another solution like the ESP8266 that you can program with Arduino IDE, and you have in this microcontroller you have a Wi-Fi unit which is included, and you can program this component as a mobile device, but also as an access point. So if you want to use a Wi-Fi signal in order to do localization inside the building, you need to have an accurate propagation model for an heterogeneous environment. But this is very difficult to have, and the pseudo-range distance are quite difficult to be sufficiently accurate to calculate position. The other way is, which is easier, is to build a map of the signal strength inside the building. So this map is mainly called fingerprinting map. And in this type of map, so you need to collect some information before you are going to use your indoor location, because all of this information will be used as input in order to calculate the position, because you need to realize relationship between signal strength and the position inside the building, and then you are going to use this relationship in order to compare your reception values to this information in order to know where is your device inside the fingerprint map. So the main drawback of this way is that the fingerprinting map is quite long to build. So it takes some time, and it is also a good representation for one time. But when there is more people, less people inside the building, this fingerprinting will be more or less accurate. So this is the main drawback of this solution. So how can we improve this fingerprinting? So we develop a solution in order to avoid this manual step, this manual initial step, which is about building the input data for the system. Our idea was to make this input information fully automatic in order to have something which is plug and play, more or less, which is quite simple to use for non-expert, non-specialist. So the idea is to define, to qualify the area permanently, not only at one time, but all over the day, every day, in order to improve the system on not having a negative derivative of the accuracy along the time. So access points are located at known coordinates. The environment quality is estimated for each link between two access points. So the idea is, because access points are static on the same condition, we are going to have always the same signal strength measurements between each two access points. But when it changes, it means that there is a door which are open or closed, which are because people are moving inside the building, etc. Many reasons that the environment quality can be modified. And because we are calibrating the signal strength received between any two static points, we can have some interesting information in order to build this virtual fingerprinting. So this calibration function is not only run at the beginning, but permanently, regularly, all over the day, in order to have a good estimation of the area. So if you want to use integrity, it's also possible, but you need for that more than 3 access points, and I will explain a little bit more about that on the next slides. So when you deploy an infrastructure, you need to know if you are going to use a long-term positioning system, or you are going to use a short-term positioning system. So if you use a long-term application, so you need to locate your access point inside the building, connected to wires inside the building, and to fill the coordinates of each access point manually. So for the short-term use, it's easier to put the access point outside, because when you put it outside, you can receive satellites, and then you can calculate latitude and longitude using the GPS device. And then from this position, you can also define in a second step distances from this outside access point on the mobile device inside the building. So this access point will be self-powered with a battery and without any wire, because you don't have time to deploy it. It's only for short-term use for firemen, for example, or soldiers. So if the outside access point need to measure distances between each other, it's also possible using ultra-wideband or differential GNSS or infrared light, for example. So now let's take a little time about a system we developed at the lab, which is called Open Wireless Positioning System, which is OWLPS. It is made of Fonera Wi-Fi access point, including a MIPS processor with 200 MHz frequency and only 8 MB of flash for all the system. What is interesting in this hardware is the Atheros chipset, which allow to use a driver where the access of the received signal strength is quite easy. So we can use with this piece of hardware a library called RadioTap, which allow to have information about the signal strength for each packet received. So it's very interesting information, very detailed. It is very interesting to use that. So what is trilateration? Trilateration means that you have at least 3 access points on the plan, and you can define some distances between the mobile device on one access point. So the full circle is the real distance from the mobile device to any of the 3 access points, and there is only one point where the 3 circles cut in one point. So this is a real position, but in the real world, you are not going to have this exact distances. You are going to have approximate distances on the dotted line of the circles is what you measured, and what you measured is not one at the end. The intersection of the 3 circles is not one point, it's a small area, and if this small area is quite short, that means you have accurate measurements, but if this area is quite big, you can have some doubt about the accuracy of the result. So, what I forgot to say, if you have 3 big circles, you are always going to have you are going to have an area as an intersection. But if the 3 circles are too small, the problem is sometimes you have no area at all, because the intersection of 2 circles is nil. So this is quite a problem. This is why we don't use this basic system. In fact, we use bisector lines, and for each couple of access points, we define a weight which allow the bisector line to be closer from one access point to another one. Like this, you can respect the differences of signal strength. And if you have 3 access points, you are going to have 3 couple of access points. And then you are going to draw 3 bisector lines. And if you have a very good system, or you have some chances, you are going to have only 1 point, but mainly you are going to have a triangle. According to the size of this triangle, your system will be good or not. You are going to have a good confidence, or you are not going to have a good confidence on the results. So if the area of this triangle is small, you are going to have a lot of confidence. If the triangle is very big, you are not going to have a good confidence. So this will conduct also to a sort of accuracy, a sort of dilution of precision. So this is how we can define the dilution of precision. So if you have more than 3 access points in their area, let's say you have 6 or 7 access points, maybe you can combine differently 3 access points, and you are going to have as a result a big triangle for 3 access points, but for 3 other probably you are going to have a smaller triangle. And like this you can select the best 3 access points in the area according to the mobile device location. So with this method, if you have more than 3 access points, it will be easier to guarantee and to calculate the integrity of the results. So let's see what type of wireless network we can use in such applications. So we can use mobile cellular network, because there is GSM, 3G, 4G, 5G, etc. We have also Wi-Fi network, as I said, and we have 2 frequencies, 2.4 and 5 GHz. We have also low power wide area network such as LoRa and Sigfox, and we will do some exercise, some practicals about LoRa using some modules. We will see it later. We can also use Bluetooth network, like for identifying proximity of people using Stop COVID application, for example. You can use also RFID and ultra-wideband frequencies. So, what can be done using a mobile cellular network? It will be an integrated function inside the base station, and it can be also by sending reception report to the user device in order to collect information about the area of one smartphone. So about the Wi-Fi network, you can have some information which is called RSSI, Received Signal Strength Indicator. It is normalized for the connected access point, but not for access point in the area, not all the access points. So we need to link this information to a packet which has been received, and it is quite hard to do that, because it's not quite easy directly. It's not very easy to do it on some device, it is not allowed to do that. There is no norm to do that. It's not fully it's not dedicated. So for the Bluetooth network is nearly the same as the Wi-Fi, but also it's only for short coverage. The Bluetooth coverage is very small compared to Wi-Fi. So for ultra-wideband communication, in fact, you need to send a pulse on a wideband, something like 500 megahertz, in order to have a good accuracy of the time of the pulse, in order to have an accurate time of the signal. It was not allowed to do some research until 2002. It was not allowed for civil utilization, no authorization. It was before this date, it was dedicated to military use, but from 2002 now, we can do some research on such type of wireless signals. There is a norm, there is a standard, which is 802.15.4a, and the coverage of this signal is something like 10 to 15 meters, and it's only on line of sight. And if you are on line of sight, you are going to have something like 5 to 10 centimeters of accuracy. So, what type of positioning model we can have inside a building? You can use theoretical propagation model, but you can also use model using signal strength measurements using fingerprinting, for example. But you can also do geometric model according to the type of the building, and at the end you can use hybrid model, a combination of two of these three models, for example. So what means theoretical propagation model? For example, it can be the Friis equation. So the Friis equation is the power of the reception, the power of the transmission, the type of antenna, the gain of each antenna, reception, transmission, and then you have the wavelength of the frequency and the distance between the transceiver, and the transmit unit and the reception unit. So it is a good formula in an open environment, but very difficult to use this formula in an heterogeneous environment. So if you want to use a signal strength map using signal strength measurements, you need first to have a calibration of the building, fingerprinting, because if you don't have this information as input, you cannot connect a location with a signal strength, because the signal strength is very, very variable, very, very difficult to calculate, to identify inside such type of environment, which is heterogeneous. So this information must be stored in a database, and at the end the accuracy will be something like 2 to 5 meters, which according to the application can be enough if you want to do something with a better accuracy. You need to use more techniques, more hardware, etc. It will cost very more to have a better accuracy. So what is a geometric model? A geometric model you have the the map of the building, you know exactly where are the walls, where are the doors, and you are going to use a propagation model which will do something like ray tracing in order to simulate all the physical phenomena inside the building, in order to define that in this part of the building you are going to have a very good reception, but if you are in this part of the building it will be not good. So in good condition you are going to expect something like 1 meter of accuracy, but only if the conditions are not changing, if there is people inside, for example, if there is doors which are open or closed, and this is not simulated in the initial model, you are not going to calculate accurate position. So as I said previously, in a bidirectional network, you can receive information on the mobile device, which is a centralized solution, or in the infrastructure, and it's a distributed solution. So if you want to integrate the localization function inside the mobile device, you can use the normal report, you can use a dedicated piece of code in the Wi-Fi, and the target application will be to deliver location service to the device, like navigation, for example. And the other way is to monitor where are your authorized devices, because you need to know the address of your mobile devices, and you need to add a piece of code inside your devices. So in the opposite, when you integrate the positioning function in the network infrastructure, it will be on the base station or access point. It will be a distributed measurement, so you need to centralize this information in order to compute a position. So you need to have a dedicated piece of software inside the access point, but you don't need any piece of software in the mobile device if the mobile device is sending something on one frequency. It can be used to calculate its location. So the target application is also service for the device, but also it can be to realize some security in the building and to detect intrusion of unknown mobile device, for example. So it's really interesting to have this architecture, this structure, in order to protect buildings. So this is the platform we built in our lab with OWLPS. So it's an infrastructure-centric technique. So that means the mobile phone here will send a packet which will be received by the 4 access points. On this information will be centralized on the aggregation server, which will deliver this 4 signal strength information to the positioning server, which will compute coordinates or location of the mobile device, and it will go back to the mobile in order to deliver the calculated position. So what are the advantages of OWLPS? So it makes the calculus inside the network infrastructure. So like this, you have an accurate position of your device using periodic signal if necessary. You can also have positioning of unknown device or hostile device without any traffic injection. And also, finally, you are going to have some signal strength variation observation between Wi-Fi access point And like this, you can identify maybe some indoor movements without any device, because you can observe, you can monitor some variation on the received signal between each Wi-Fi access point. So finally, the access points are inside the building, and also you can deploy easily access point outside the building, near the building, of course, and using this you can have also short-term application. So how can we compare all of this positioning system which can work inside or outside? So this is a global view with accuracy on the x-axis, on the indoor-outdoor information on the y-axis. So you can understand that GSM on the left is not very accurate compared to ultra-wideband, which is very accurate, but it works only on short distance. Ultra-wideband can be used inside or outside, because you have to deploy your own devices, but for GSM on the left, you cannot see GSM because there is GDOP above, but it's GSM on the left, the gray line. So for GSM, you don't have permission to deploy GSM base station inside the building. So it is working well outside the building, but it's not working well inside the building. This is why you can see that there is here a decrease of accuracy for the GSM. So for GPS, it's better outside, but it also sometimes working a little bit near from the outdoor. If there is a window, if you are near a window, for example, but when you are very inside the building, it will not work anymore. Before it will stop before the GSM, for example. At the opposite, the Wi-Fi is working well inside the building, but it's not deployed outside. So when you are outside, you are going to be far from the building, and when you are too far from the building, you are going to have no accuracy. DGPS is also good outside, and you have more accuracy than the simple GPS, but it's also not working very far inside the building. So if you want to have continuity of the positioning service, you are going to have a way to combine two solutions, one for outdoor, one for indoor, on trying to have something which can link these two solutions. So you have two possibilities: switching solution or combining solution. And if you want to do some switching, you have to decide when you use the outdoor system, when you use the indoor system, but you cannot use both of them at the same time. At the opposite, when you use combination, the idea is to activate the two systems at the same time, and then using part of the information in order to have a final position which in a way combine the indoor and outdoor solution. Let me show you an example. So this is a view draw where you can see here it's an outdoor, fully outdoor system of location here using only satellites. And maybe here we have only Wi-Fi system in order to compute a position. And sorry, it's this draw. And the idea is to use when it's possible, when you have not more than 3 satellites, you can use one Wi-Fi access point. Sometimes you have 2 satellites, 2 Wi-Fi access points. This is a sort of a combined system which can allow us to improve the calculation if we don't have enough satellites to compute an outdoor position, and if we don't have access to enough Wi-Fi access point in some specific area between outdoor and indoor. Maybe it's better to combine both of the information. So this is also an example to illustrate what can do a combined system. So on the red line here, you can see that there is the urban canyon effect, because you have building on the left, on the right, there is a street here, so you can receive only 4 aligned satellites. So when you are in such a configuration, you are going to have a good accuracy in the axis of the satellites, but in the perpendicular line, you are going to have less accuracy. So it's not the same level of accuracy. So first, if you use only 4 aligned satellites, this is the true line. The true trajectory is with the blue line, and the estimated trajectory with the green dot line. So as you can see, here we are close from the true trajectory, but when we are on the vertical axis, you can see that there is some error, significant distance between the real and the estimated that you cannot see here. Why? Because the error is on the horizontal axis here. So when the point is located here, but the real position is far back or far forward, you cannot see, because you know that at one time we were at this position, but was it at the right time? We don't know exactly, and we can see this error here, which is quite difficult to identify here on the horizontal part. So now, if we use, to illustrate what is combination, if we use the 4 aligned satellites, which deliver not well accuracy, if we combine it with 2 access points, we can manage to improve the signal. And as you can see, the green dot are quite close to the real trajectory, but we still have more errors here than here. Of course, because at the beginning, this accuracy, this vertical accuracy, were better than the horizontal accuracy. But we improve a little bit the horizontal and the vertical, but we cannot compensate everything. But at the end, the mean is better with 2 additional Wi-Fi access points. So now, according to this scenario, so how can we guarantee that we improve the accuracy of the satellites using this access point? There is also an evaluation function which is needed to have information about the quality of the precision, which is geometric dilution of precision. So of course, the DOP it does not include all of the type of errors inside the location calculation. So how can we calculate the GDOP? The GDOP is the formula when the value is close from 1, between 1 and 2, it's a good level of accuracy, and when the GDOP is greater than 3, it means that you don't have a good accuracy. On the 2 draw, you can see what is a good DOP. A good DOP means there is long distance between each satellites. If the satellites are too close from each other, you are going to have a bad GDOP. Okay? So when you have a lot of buildings, you are going to have less choice on the satellites. So if you have less choice on the satellites, you are going to have closer satellites, of course. So what can we conclude? As you can see, there is a lot of work which must be done on signal strength, on time of flight, in order to improve indoor localization systems. We need to integrate also these technologies in a combined system in order to have continuity of the positioning service, because we need to have a positioning service which is working well inside and outside, and the users don't want to know how it's possible to have something like a position at any time we want to have a position. We don't care about we are inside or outside. We need to deliver something which is accurate. So there is also a lot of improvements which have to be done in combining at least 2 solutions, one for outside and one for inside. And probably we need also to do additional work on the combination of Wi-Fi with inertial unit, or GNSS with inertial unit, or Wi-Fi with SLAM, etc., etc. Thank you for listening.